So if you graph the function x minus 6 over x squared minus 7x plus 6, you get what you see on the calculator. But rational expressions are a little bit tricky. What we mean by rational expressions is a polynomial divided by another polynomial. So you have like an x squared on top and an x to the third on bottom. And funny things happen when you do that. So if I draw the graph, it's going to look like this and like this. And you'll notice there are two lines that the graph gets closer to and never actually reaches. Those are called asymptotes. We should probably beat up the person that came up with that word, because it's hard to spell and even harder to say. So an asymptote is the line that the graph approaches. So this one has a vertical asymptote and a horizontal asymptote. So the horizontal asymptote, what is the equation for that line right there? What equals 0, the x or the y? The y equals 0. So we have a we have a horizontal asymptote at y equals 0, because it goes through the y-axis at 0. Yeah. All of these points, like -10, 0, -5, 0, -1, 0. So that's the line when y is always 0. Okay? So we say the HA, or the horizontal asymptote, is y equals 0. This one we would call a vertical asymptote at x equals 1. There's another type of asymptote. It's called an oblique asymptote, and it might look like this. So you could have a graph that went like and on one side it gets closer to the dotted line, and on the other side it goes through. And sometimes you actually go through an asymptote, usually near 0. But you can go through it. The asymptotes only really matter on the far ends of the graph. So an oblique asymptote is one that's got a slant to it. Okay. So looking at this graph, if I wanted to tell you what the domain was, well, rational functions, rational expressions always have all real numbers except for a few points. So the domain here is real numbers except x cannot equal what value? There is an x equals 0. It's right here. 1. X cannot be 1. Why is that? Right, so on the graph you can see it doesn't reach the 1, but why be so mean to the number 1? What did it do? It doesn't belong in the function. Why does it not belong in the function? Well, let's plug it in. Let's plug in 1. So 1 minus 6 is -5. Plug in 1 here. 1 minus 7 plus 6 is 0. What's wrong with that? You're not allowed to divide by 0. And by the way, what is dividing by 0? Infinity. Not 0. Do you want to know how do you divide a number and get a 0? So 5 divided by what is 0? How many times do you have to, how many pieces do you need to cut 5 into in order for each piece to be 0? An infinite number. So they kind of go together. 1 over 0 is infinity, and 1 over infinity is 0. And we do that in calculus all the time. Because if you had a ruler and each piece was length 0, how many pieces would you need to create the ruler? An infinite number, right? Well, if you had a ruler and you cut it into an infinite number of pieces, how big is each piece? 0. So they kind of go hand in hand. So you can see the trouble with 1 is it's way up there at infinity. It's also way down there at negative infinity, but that's kind of beside the point. So if 1 doesn't work, are there any other numbers that don't work? Well, let's check. The trouble is, if the bottom equals 0, then we have to throw those numbers out of the domain. So let's look at the bottom. So we look at the denominator. When does this equal 0? Oh, it's a quadratic, and it equals 0. What should we do? Factor it. So x minus and x minus. Are there numbers that add to be 6 and, or multiply to be 6 and add to be negative 7? 6 and 1. So we know x equals 6 doesn't work. What about x equals 1? We already knew 6 didn't, right? Or no, sorry, we already knew that 1 didn't. What about 6? Well, let's look at the graph. 1, 2, 3, 4, 5, 6. It looks like it's there, but let's try it. Second, calc, go to value. I'm going to plug in x equals 6, and it gives me blank. So there is a little gap, 1, 2, 3, 4, 5, 6. Right here is a gap we call a hole. So the function does not exist at 6. So if I go back up to my domain, the domain is all real numbers, but x is never 1, and x is never 6. Everything else works. We can guarantee, if it's a rational expression, that everything else works. Okay. Well, now the question is, how come the 1 was a vertical asymptote and the 6 was a hole? How do we tell the difference? Look at the original function. Do you see anything that we can do? I can cancel the x minus 6's. Okay? Cancel this, oops, and cancel that. And I'm left with 1 over x minus 1. If the factor cancels, it creates a hole. If the factor does not cancel, it creates an asymptote, a vertical asymptote. So your job today is to find the domain, and then you need to list this is a hole, and this is a VA, a vertical asymptote. That's all you're going to do today. If it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote. Okay? Well, put your pencils down for a second. Okay? Well, let's talk a little bit more about holes. So let me back up. Okay, so if I write that equation, this equation simplifies to be 1 over x minus 1, right? Everybody agree? Come on. Okay, so what's the difference between these two graphs? There's one difference. The hole. That's the only difference. If you were to graph this one or you were to graph either one, they look exactly the same. The only difference is the hole. So the original one has a hole and the second one does not. Okay? So if I had something like x minus 2, x minus 3 over x minus 3, and these cancel, then the graph is just x minus 2, which is linear. So it's a straight line. In fact, it's this straight line. So that graph looks like this. What does this graph look like? It has a hole at 3. So 1, 2, 3, there would be a hole right there. So that's kind of important. If you have a rational expression and you simplify it, if you simplified it, then you plugged those holes. And you need to remember that those holes are actually there. The calculator doesn't know the difference unless you ask it for the hole. Otherwise, it's not going to tell you. But a rational expression and its simplified counterpart graph exactly the same. The difference is the simplified version is going to plug the holes. The asymptotes are going to be there no matter what. But those holes get plugged whenever you simplify. Okay, so let's do another one. So right now, all I want is the domain. What is the domain? And if we have to throw out numbers, you have to tell me what numbers we throw out and why. So I factor the bottom. What do I know about the denominator? X minus and x minus. Minus 4, minus 2, okay. So the domain, I already know that the domain is all real numbers, but x cannot be 4 and x cannot be 2. And does the top factor? X and x minus and plus 4 and 4. So I can cancel the minus 4s. So what does that tell me about this point? That's a hole. What can you tell me about that point? That's a vertical asymptote. We'll get in that tomorrow. That's the range. Right. A graph can have lots of vertical asymptotes, but it can only have one horizontal. So the range is always all real numbers except if it has a vertical asymptote, and they don't always have one. Well, technically they don't always have one. But you end up throwing one number out of the range. The trouble is it's a little bit harder to find because sometimes it's horizontal and sometimes it's oblique. The horizontal is pretty easy, but the oblique takes a little bit more work. All you're doing today is this. Now, on page 60, you have a whole bunch of problems. So we're going to do number 1 and leave more space because we need to calculate the range. We need to calculate, what's that? It is 90. What did I say? Sorry, page 90. So leave a lot of room because you still need to graph it. You still need to find the horizontal or oblique asymptotes, which will help you find the range. So look at page 90. We'll do a couple together. All right, page 90. So look at number 1 on page 90. Okay. So what is the domain of number 1? All real numbers, but x cannot be -7. That was easy. Is that a hole or a vertical asymptote? That is a vertical asymptote. Now, you need to leave room for a graph, and you need to leave room to do other calculations. When we come back Monday, that's what we're going to work on. I would skip down 4 or 5 lines to do the next one. You need to have a graph. We need to calculate the range and the other asymptotes. Okay? All right? So that was pretty easy. Let's skip to number 3. So on number 3, I need to factor the bottom. How does it factor? X minus 4 and x plus 4. Do any of those cancel? No. So what's my domain? All real numbers, but x cannot be 4 or -4. Are those holes or vertical asymptotes? They're both vertical asymptotes because they didn't cancel. So both of those are VAs. That will play into the horizontal asymptote. Yeah. So it's good to factor the top because you're going to need it later. And that x minus 5 on top is going to factor into finding the other asymptote, the horizontal or the oblique. Sometimes it's horizontal and sometimes it's oblique, but it's never both. Okay? All right. Let's do number 10. Number 10 is kind of hard. So, I certainly need to factor the bottom. Do I need to factor the top? Yes. But if you factor the top and nothing cancels, you didn't waste your time because you need to factor the top in some cases in order to figure out the rest of it. So number 10. So let's factor the bottom, negative 12x squared. Now what am I looking for? I'm looking for two numbers that times to be negative 12 and add to be this middle 4. Plus 6 and minus 2. So I rewrite 3x squared plus 6x plus minus 2x minus 4. Now I group. Can I pull anything out of that first set? 3x. What's left? X plus 2. Can I pull anything out of that second set? Negative 2. What's left? X plus 2. So on bottom, 3x minus 2 is one factor, and x plus 2 is another factor. Okay. And now I need to solve the top, right? So I'm going to erase all this. So I multiply the top, and I get 42x squared. So factors of 42, 1 and 42, does that work? No. 2 and 21, does that work? Nope. 3 and 14, does that work? Yes. So I rewrite 2x squared plus 3x plus 14x plus 21. Okay. Well, what can I pull out of the first set? What am I missing? This was the sort of thing that got Jackson moved. So I can pull out an x, 2x plus 3. What can I pull out of the second set? A 7. So plus 7, 2x plus 3. 2 does not go into 21. So my factors are x plus 7 and 2x plus 3. Does anything cancel? No, but we will use those, the top values, to find our range. Well, kind of. You'll see tomorrow, or Monday. Okay, so my domain is all real numbers, but x cannot be negative 2 or 2/3. So if I set this second one equal to, or the first one equal to 0, I subtract the 2 and I divide the 3 and I get 2/3. Wholes or vertical asymptotes? So those are vertical asymptotes. Okay, let's do one more together. Let's do number 14. So for number 14, can I factor the denominator? How? Pull out an x. So x times x plus 3. Does anything cancel? Yes. The x's cancel. So my domain would be all real numbers except x cannot be negative 3 and 0. Whenever you have a solitary x, the root of that is 0. So what we did was tossed out the 0. So negative 3 and 0. Negative 3 is what type of? Yeah, it's a vertical asymptote. And 0 would be a whole. So The original graph is exactly the same as the graph 2 over x plus 3, except the original graph has a hole at 0. All right? Okay, so go through on page 90, 1 through 21. Leave lots of space. All you're doing today is finding the domain. On Monday, we'll find the range, and that will help us find the asymptotes, the other asymptotes. Good luck.